was fairly pleased with how it went last time, so here we go again. Now, I want to give a quick shout out to Olivia. Are you here, Olivia? There you are. All right. So Olivia has contacted me about this really incredible heroic thing that you're doing. All right. I just, I wanted people to know about that. So, and I watched your I Can Do It video, and it seemed to, anyway, it was like that there was even more. So, I mean, it was really, I really enjoyed learning more about you. But the thing that you particularly contacted me about, that I was proud of everything you were talking about, all the stuff that you're involved with and all the service that you do. But Olivia started, she founded a nonprofit called Lights for Kids. And would you mind shouting out what that is?
Yeah, so Lights for Kids is a nonprofit organization. I founded. We collect and donate these sets of string lights, like what you see on the outside of the houses and stuff like that, as well as joinery items like toys and coloring materials and stuff like that to children's hospitals across the country. We currently work with 34 children's hospitals in 25 states.
Yeah, that's and you told, and in your email, you told me a little bit about, what prompted you to do that. And I thought that was just, I mean, your inspiration for doing it was also neat. So I don't want to, you tell that story. I don't want to try to.
So around 7th grade, I started having issues with my knees. And by 8th grade, I really couldn't walk. And I had major surgery in December of 2016. And the winter holidays are my favorite time of year. So like I was decorating my room, and when I went to the hospital, I brought my set string lights off my wall, and I had my mom string around my hospital bed while I was there because it's major surgery. I had to fix it. And then I left the lights with the little boy across the hall when I left. And the lights just helped me a lot. They, like when my parents were there, I was a little less like in the dark and alone, because even though it's like a children's hospital, they still like don't decorate the individual rooms. So it just brought my room like a little more cheer for that time of year. It also helped the nurses see at night that I had to turn on the lights and wake me up 2 hours and they would check on me. So in fall of 9th grade, I decided that I wanted to collect string lights that year and donate them to the hospital where I had my surgery. And it was a project that really took off. And I've been doing it every year since. We are 6th year.
Yeah, wow. 6 years. Oh my gosh.
We've donated over 4,000 lights.
Man.
And over 500 joy bringing units.
Say that last part again?
Over 500 joy bringing units, which is a new thing that we started doing last year.
Wow.
And I typically work with my high school, but I also work with local businesses in my community back home to host collection drives and fundraisers and things like
That's
that.
amazing.
And then it's a lot of it's ran by me and my mom, and my sister helps out a lot.
Wow.
And I still do like an in-person drop off of donations to the hospital where I have my surgery.
Oh, that's incredible. Wow. Yeah, that deserves another. So it sounds like it's gone. It's not just local anymore. I mean, you started locally with that, but how far extended is it now?
I'm working with some people here in Cincinnati right now. One of my professors last year, this year, Professor Weiler from the Criminal Justice Department, she fell on the project, and I've done a couple different speeches down here, and she helped collect some donations down here that I was able to take home with my dad's truck last year. So I work with some people down here, and I'm currently working with the ECH marketing department, and they're developing a story about it. And UC Housing, which I work for, they are interested in donating and stuff like that. But we've also worked on expanding past just my city for family communities involved. And as far as donations, we're in states as far as like Washington and Oregon, like over in the west, and then we're all the way up to New York, and the east, Texas, and south.
Man, that's incredible, Olivia. So, man, it just blows me away. And as I trust you all know, I have this theme of heroism, and especially in my intro class, and just in my own interests, and that's right up there. I mean, that's one of the most heroic things I've heard a student doing. And you've been doing it for 6 years. It's amazing. It's incredible. So thank you for doing that. And wow, yeah. So I don't know if you want other people to get involved with you, but now you all know. So wow, keep up that awesome work. So, and especially it must be really this peak time of year for that kind of, I mean, it started with you with holiday lights, I think you said, and so yeah, but I'm sure it's a year-round thing, but it must be peak time right now. So good job. All right. So thank you very much for sharing that. In the recording here, I have no idea if I suspect none of that got picked up by a microphone. So I may have edited that out. So all right. Unfortunately, that might not have made it into the video. Big announcements. I don't have any. It's Wednesday. Okay, it's week 11, and we're making it. So hang in there, everybody. Next week, I think is it an exam week? I don't like to get caught by surprise anymore, but I'm pretty sure it is. So something to look forward to. All right. Anybody got any questions about anything before I try to wrap up this chapter? Ask now, or I'm gonna talk. If there's anything in this chapter in particular that you have questions about, put you on the spot. Raise your hand later, or let me know if you do. Okay. I want to take a few minutes to wrap up talking about long-term potentiation, because that can be confusing a little bit, and so let's see if I can do that. And then I hope to have more time to talk about patient HM, which we've covered a little bit during the first weeks of the class. So we'll come back and revisit him a little bit more. All right, so anyway, long-term potentiation, there's 4 stages of the synaptic plasticity that's involved with that. And real briefly, those are, there's a generation phase, I'll come back. The generation phase, a stabilization phase, a consolidation phase, and a maintenance phase. I want to try to disentangle that a little bit. So long-term potentiation is kind of, it's not really clear how long it takes or how long it lasts. There's something long-term about it, hence the term, long-term potentiation. So it can, some of it happens in just the first seconds of stimulus exposure, and some of it can go on and last for an indeterminate amount of time. All right. So anyway, a first part of it is very, very brief and tends to be very temporary. So like within the first minute is sort of this generation phase. So we covered last time, this kind of phenomenon where, the glutamate NMDA receptor is a well-researched, good example of the long-term potentiation process. And how this is kind of a complicated receptor system, and not just a simple excitatory or inhibitory, ionotropic receptor. There's a metabotropic component to it, which is the long-term potentiation. All right, so it involves, a couple of different kinds of receptors, and then the growth and maintenance of these receptors, and about sodium and calcium ions in particular, flowing into the postsynaptic membrane to pass the messages on, or make the messages persist. All right, so covered that a little bit already.
Welcome.
I'm not going to go over that again. So that's the generation phase, is the entrance of starting with calcium, hitting that AMPA receptor, and that provides some positivity that's going to affect the NMDA receptor. And when it reaches a certain critical level, there's not depicted here, but there's a magnesium ion that's kind of glomped onto this thing at rest. And it'll, it causes that protein to shift. Everything about proteins is their shape, right? Protein's shape is its sort of destiny. And so this positivity coming in from calcium, from the AMPA receptor, is going to stimulate that other NMDA receptor to shift a little bit, let go of that magnesium ion that's blocking its channel, and it's going to let, I might have this backwards. So sodium was rushing in, causing that initially. My memory's a little, my long-term potentiation hasn't occurred here. I'm going to go back and look at the previous slide because all right, I did have it backwards. So sodium's associated with the AMPA. I had it reversed in my mind. So sodium came rushing in first, caused that positivity, caused that magnesium to pop out, and then calcium can start flowing in. And then that process, that extra, excitation is going to start a second messenger system. So this other protein kinases start to form. And these are enzymes which are going to go on and cause other things to happen. All right. And so there's a variety of other things that they do. Some of them, some of it gets transported retrograde fashion back to the presynaptic dendrite and causes some change, some long-lasting changes there. Some of those changes are going to cause additional AMPA receptors to form, which is not depicted here, and so on. All right. So anyway, that's that temporary short phase part of it. So you have the additional receptors are going to start to get inserted into the synapse membrane there. All right. And then for 15 to 20 minutes or so, there's also some shifts to the dendrites. The dendrites start to get these little, they get spikier, they get a little bit more firm, they get, they're strengthened. All right. So, part of this process is about, strengthening literally physically strengthening the synapse. All right. So, it's going to be more successful if it's physically capable of maintaining itself. So they get these dendritic spines that we see, that start to develop in just 15 or 20 minutes. All right. So that's sort of what we call the stabilization phase of this process. All right. Then for the next several hours, the consolidation phase will happen, and more and more proteins, are being developed and are contributing to more and more of the stabilization that we see there. Then lastly, and this is we don't know how long this lasts. This might be, we don't know. Yeah, Tanya.
This might be my question, or maybe it's the textbook and I didn't see it, but what age does synaptic plasticity stop?
What causes plasticity? What causes neuroplasticity to stop?
At what age does synaptic plasticity stop?
It doesn't really, but that's a good question related to this a bit. So neuroplasticity in general is, just young children seem to exhibit that to a greater degree. It will persist, but I don't know. That's a good, when does it get reduced? I don't know. It's,
I used to be in the fitness industry. So before I came back to college, I was at a convention in San Diego, and there was this woman who did a program called, I think it's called Ageless Grace. But anyway, her whole thing was having a bunch of senior citizens sitting in a room, imagining themselves playing instruments, like air guitar and things like that. And she had this whole program based on improving senior citizen neuroplasticity through music.
Yeah. So another, if I could, if I can jump in,
I mean, their right foot while moving their left hand, do these exercises.
Right. Yeah. So it can be strengthened. It can be, it can be, it begins to fade as you age, like everything, and it can be strengthened with some therapy. Yeah. So I don't have pretty sure there is no even little critical window where it closes, but young brains are more plastic than older brains, but just like every other development or maintenance of the body, training, some therapy can prolong.
So like
that.
say that synaptic plasticity for whatever reason starts to fade when you're a kid, like due to whatever disorder or whatever illness you have. Does that mean that can be
Can it be brought back? I mean,
Yeah,
that's a really good question. I don't know. I'm just speculating. I don't know. I'm guessing yes. I'm guessing that it can be. I'm just speculating. So it's like anything, like muscle tone and muscle growth. I mean, you can lose it and you can build it back. I mean, so I think I'm just guessing. I don't have expertise on that. Yeah. So good questions. So anyway, this maintenance phase, which goes on maybe years, I don't know, involves, this is a pretty new development, 10 to 15 years, maybe, I'm guessing. The substance called protein kinase, PK zeta. It prevents those AMPA receptors from diminishing or being removed again. All right. So I'm gonna show you that was the next video. Okay, I hope it's coming.
Long-term memory actually involves an anatomical change.
All right. So anyway, this video is about patient HM in Jacopo. I showed you the first half of this video in the first days of the semester. I might come back and watch a little bit later today. But anyway, this is like the middle of that where they talk about research with PKM zeta. All right. So, and this is, I've mentioned him before. This is Eric Kandel. All right. So Eric Kandel is a neuroscience, god and legend, and he did some of the early work with aplesia, and so anyway, you get to hear briefly from him. So that's what I also like about this video.
So long-term memory actually involves an anatomical change in the brain. So as I like to say, if you remember anything about this conversation tomorrow, it's because you will have a slightly different head than you had today.
But what maintains a long-term memory? How can you recall something that you may not have thought about for 20 years? Neuroscientists Todd Sachter and Andre Fenton think the answer may lie in a molecule called PKM zeta that accumulates at synapses as memories form.
PKM zeta acts as glue, if you will, for fixing the connections amongst the neurons that were active together, so that later in time, those neurons are bound together and permanently bound together and can become active again to recall the experience.
To assess the molecule's importance, Fenton set up an experiment that would give the rat a memory. He placed it on a revolving table, where in one area, it would receive a mild shock.
There's the rat, and he's approaching the shock zone. He's beginning to move a little bit, but looks like he's going to enter the shock zone. He's gotten shocked, and he's just run away. He's approaching it right now.
Soon, the rat always avoided the shock zone.
And he's walking away. So when the rat stays away from a particular area, we can imagine that he has remembered where he was shocked.
Then, Fenton injects the rat's hippocampus with a chemical called ZIP, known to undo the effect of PKM zeta.
And what we observed, which was quite remarkable, was the rat acted as though it had forgotten completely where the shock zone was. And it explored the arena as if it was in the arena for the first time. Just got shocked.
Yet, the rat could learn once again to avoid the shock zone.
So we hadn't damaged the rat's brain. We hadn't broken its ability to learn anything. What we had simply done was specifically erased the memory for that shock zone.
Without PKM zeta, the rat cannot maintain a long-term memory. While this is not the only molecule active at synapses, it does appear we may have found a crucial ingredient of memory, one that explains how a 3-pound lump of flesh can store, indefinitely, vivid recollections of everything from birthdays to weddings to episodes of Nova Science Now.
So that's pretty fascinating stuff, I think. All right. So, again, that zip that they inject just seems to inhibit this PKM zeta protein, and it doesn't have any other effects. It's not like it's this zip is a drug that, it somehow, alters the mind in some other sort of way or has other effects. It just selectively shuts down the development of this particular protein. And as you saw, it results in a lack of ability to lay down the memory. All right. So it cuts off that consolidating part of the long-term potentiation process. And the rat where they very quickly learn how to do that task. And days, weeks, probably months later, if you hadn't done that with a rat, shock is very undesirable. And that's something that forms a very vivid memory normally. All right, so it can just kind of turn the ability off and erase that memory, even after the rat was demonstrating that it was remembering it. Okay, so it's not just that it prevents the memory formation; it can erase the memory once it was already seemingly there. Okay, so I had skipped a couple of points I wanted to make, and I just these aren't really super important. I was just going to say that these are some of the 3 of the experimental procedures that are very often used with this long-term potentiation kind of research, involving spatial mapping. So using like, the inhibitory avoidance was the example you just saw. The rats learned to avoid this particular part of the wheel that was the area that was going to deliver shock. So it's about shock avoidance. And also, studies involving fear conditioning. All right. So spatial mapping this is a perfect example of that kind of task where rats are, natural swimmers, but they don't like to swim. They, you put them in a big tank like this, and they'll swim around trying to get out. And if you have like a hidden platform that just can't be seen, just barely underwater, if it's stable, the location of that, they'll use cues, environmental cues outside of the tank or whatever. And they'll quickly learn where that platform is and get up on there and avoid the swimming. All right. So they could have, this was another, you could have used, they have used these kind of studies to study long-term potentiation. So this PK, the study you just saw could have been done with this task just as probably readily. And other spatial memory tasks are like different kinds of mazes that they have to remember where, which arms of the maze have food and which ones don't, or which ones will deliver some, aversive thing like shock or excessive. Rats don't like bright light. Okay, so they'll avoid an area that's brightly lit or wide open. They like to be, in the corners and in the dark.
So,
okay. So anyway, those are some of the tasks that are used for that kind of thing. All right. As with every chapter, there's much more than I have time to talk about. So there's a good example of radial arm maze. You can load up certain arms with a food reward, and others that don't have anything there. And if it's a timed task, the rat's given 30 seconds to they're kept hungry. You put them in there, and they're going to want to find the food. And if they know they have a 30 seconds or something to eat what they can find, they'll very quickly remember which, if you always load the same arms, they'll not only remember which arms, are loaded and which ones aren't. Even if they were all loaded, they'll of course remember which ones they've already gone down. Okay, even if they all kind of look alike, they have ability to remember the location. All right, so you can study different agents and how they're going to affect the development and the consolidation of these kinds of memories. All right. So, and then we can also study other factors that are affecting. It's all about these AMPA receptors. Getting them loaded in there and keeping them there. All right. So for that particular glutamate system, which is very prevalent in areas of learning, it's used to study these kinds of things. So it turns out there's a couple of different kinds of receptors. And they seem to be specialized for certain kinds of learning. All right, so you don't have to remember these crazy names, but one of them seems to be important for so-called working memory or short-term memory. The kind of like these kinds of tasks, like remembering which arm they've been down, or which one they haven't. All right, and the other type of receptor, it seems to be more important for establishing more stable memories. All right, so maybe if it's if it's maybe you only load some of the arms, okay, and they have to remember, the next day or a week later, from the previous time they were in there, which arms have food and which ones don't, okay? That's not a working memory kind of memory. That's a long-term kind of memory, okay? So they've been able to tease apart the different kinds of receptors that seem to be facilitating these two very different kinds of memory, okay? So that's pretty cool shit. Okay. So anyway, lots of developments there, and now genetic discoveries, and how RNA, DNA's transcription of RNA transcription of other substances and proteins and things. All right, so we're learning about that. Okay, I gotta skip stuff. Oh, this is kind of interesting. I want to mention this briefly. All right. So there's all kinds of analogies that are often made for memory. We often use the current technology, best technology. We like to say, that memory or brains work like computers. And memory is like, videotape or a hard drive or, memory storage. We liken it to certain things. All right. So anyway, first and foremost, memory is not, your brain doesn't just faithfully store memories like a videotape. And that memory problems or memory, forgetting or faulty memory is not just a simple matter of like, well, you just, it's in there somewhere, but you're just not retrieving it. Okay. So we know that, memory is when we're retrieving a memory, we're kind of experiencing it anew. We consolidate memories and then we reconsolidate them. All right. So it turns out that when you retrieve a memory, you're affecting those synapses, and they're just as vulnerable as they were when the memory was being formed initially, when the experience was first had. And that is why we can see that each time you retrieve something, you're regenerating that experience. And you might remember it differently just as a process of recalling it. All right. So lots of studies, both biological and just psychological in nature, have revealed this to be the case. One of the preeminent researchers, she's not a neuroscientist. You might know Elizabeth Loftus. She did classic studies way back in the 70s, and she's still, I believe she's professor emeritus these days, but she's one of the foremost, memory experts, and specializing in things like eyewitness memory and testimony. And so her classic study that she's in all the intro textbooks for, and you might remember this, is that she'd have people come in and watch videotapes of like a kind of a fairly mundane car accident. Okay. And then she would bring them in about 2 weeks later and ask them questions about that event. And she discovered all kinds of, reconstructive problems that occur when the person is doing that, retrieval task. So simple things like which words she would use would shape their memory. So, she would ask them to, estimate how fast the cars were when they hit each other. All right. But she'd use different words than hit. She'd use about 4 or 5 different words. And so hit, impacted, collided, crashed. She used words that have connotation, differing connotations of speed. All right. And so those simple words would matter. Everything else would be identical. The video they watched, the time, the amount of time since they've seen it, the entire sentence of the question would be identical except for the single word: hit, crashed, smashed, collided, etc. And there were significant differences in the estimates of the speed that people said. So they were reconstructing their memory of it, and it was being impacted at the moment later by the wording. Okay, other words mattered. Like if she said, using versus the. Do you remember a stop sign, or do you remember the stop sign? Do you remember the barn in the background? Okay, there was no, there was no stop sign. I forget if it was a stop sign or a yield sign, whatever. She would say, when you say that has a different connotation than the. Do you remember a stop sign? That's asking you, do you remember if there was a stop sign or not? But if you say, do you remember the stop sign? The implication is there was a stop sign there. Do I remember it? And people would falsely, remember that there was a barn or a stop sign or a yield sign just because of the word the versus Anyway, so she did lots and lots of studies that showed things like that. And that implied that there's a reconstruction of memory at the time you're retrieving it, okay? And then and that can go on. Then these persist. So then if you ask them 2 weeks later, a month later, or a year later, about the barn, now they just not only do they remember the barn, which did not exist, but they remember it with they'll offer up all kinds of vivid, unnecessary details about it that are just wrong. Oh yes, it was red, and there were hay bales, and there was some cows out in front. They just start making up. They're not lying. They're not lying. It's just that little tweak, earlier began the process of this false memory. And Jamie, we had a good conversation about that just the other day, I think. So, all right. So anyway, this is not psychobiology, but you should watch Elizabeth Loftus's TED Talk. She's got a very classic TED Talk that we won't watch now, but I had an opportunity to see her when I was in graduate school. She came and I heard her give a talk, and I mean, she's just amazing. Interesting person. So anyway, that's Elizabeth Loftus. All right. So this is not her study, but the difference between a short-term and a long-term memory. If you manipulate, you can do manipulations to the synapses and chemicals. Close to the time of the memory, and then later, and it can cause significant. At the time of retrieval, and later on, it will cause big changes in kind of memory. Okay, so anyway, I was moving on. That was very, very micro. We were talking about genetic things and individual proteins involved, and individual receptors and things like that. Let's just take a step out a little bit and talk more. So I'm being covered by my stuff here, but some of the neurostructures involved with learning and memory. All right. So I talked a little bit about this when I talked about the brief history of neuroscience, and I mentioned people like Carl Lashley and Wilfred Penfield. They did some of the early work on this, so back then, we didn't know quite how the brain worked, and they didn't know if it was, Lashley was the guy that was working with rats, and he would train them to do something like a maze, and then take out some cortex, let them heal, put them in the maze to see if they remember how to do it, and they'd remember how to do the maze. So he'd scoop out a little bit more cortex and put them back in there, and he kept scooping and scooping, looking for what they were calling the engram. The engram was like the place where where is this memory? Where is this memory stored for running the maze? And they assumed it was got to be somewhere in the cortex. And they basically decorticized these rats, and they just never could find the location. Eventually, you remove too much, and the animal can't run a maze at all anymore. So it's not, it's not that it can't remember; it can't move anymore. Gruesome kind of research. But anyway, so this led to a false idea that okay, the brain, there is no localization of function. It's just kind of stored everywhere. And then Penfield sort of in continuing that search for the engram, was doing a different kind of study. He was stimulating the cortex in people that were undergoing surgery for epilepsy. As you well know by now, the brain doesn't have any pain receptors inside. When you do brain surgery, it's ideal to keep the person, you might anesthetize them while you're getting through the skull and the skin and all that kind of gruesome stuff. But once you're poking around in the brain, it's beneficial to have the person awake so that you can, because you never want to fuck with the learning centers of the brain. Okay, that's first and foremost. Almost nothing is more important to our humanness than being able to speak and think and use language. And so even when damage is real, right there with language, at all, if possible, you want to maintain that. So, have them awake so you can literally ask them questions and have them answer things. So anyway, he was doing that kind of, research and, using little probes to stimulate parts of the cortex and mapping what kinds of things would happen. So you start to stimulate a motor area in the back of the frontal lobe, you might see the hand twitch or the foot or, part of the body move a little bit, or the person would, if you're stimulating parietal cortex, right in the, somatosensory area, they might say, oh, I felt that little tingle in the, in my left leg or, or in my cheek when you touched there. So he began to build, map and find localization of function where certain things are. So we were kind of going back and forth between this notion of mass action and localization of function. And, that led to our modern understanding now that there's localization of function, but then there's some mass action too. So memories are distributed, in networks, not in particular regions. But then again, there's also individual neurons that we discover that, seem to be important for remembering things like, individual people. There's the so-called grandmother neuron and the Jennifer Aniston neuron, and identified individual neurons that they can stimulate and or that are become active when a person is exposed to a picture of the person who's that neuron is storing. So it's an interesting collection of both distributed and localization of function. So it kind of points back to the early work by Lashley and Penfield, kind of doing similar methods, completely different methods, doing a similar kind of search. Okay. Back to classical conditioning. Lots of studies have been used classical conditioning to try to find out different structures and systems that are supporting that kind of learning. And a lot of the research has pointed back to this really interesting part of the brain, the cerebellum. All right. So I'm getting more and more fascinated by the cerebellum over the years. When I started, when I took the equivalent of this class back then, it was real simple. We said the cerebellum, that was just like, kind of basic movement. Okay. It takes over like automatic things like riding, walking, dribbling a basketball, just stuff that you used to have to think about, when it becomes kind of automated. That was the role of the cerebellum. Done, move on. Okay, that's about all we learned. It was interesting looking. It's kind of a cool looking part of the brain, and that's all we thought it did. It does so much more, and not just, in classical conditioning, it's pretty basic kind of learning, but, more and more higher level kind of cognitive tasks are being identified as having a major role in the cerebellum. Some are even speculating it's got, this mad search for consciousness. Many researchers are pointing to the cerebellum as playing a major role in this, level of consciousness. All right. So, the cerebellum. So this early work on classical conditioning identified, little set nuclei inside of the cerebellum that are important for classical conditioning. So, some of the earliest work was done with rabbits, and you puff, you give a little air puff to their eye, and and you'd have the same thing happen to you. If I puff a little air in on your eye, you're going to blink. All right, and that's a simple reflex, and just about any simple reflex like that can be easily classically conditioned. So if there's a stimulus like a tone or a bell or whatever, something that happens just before the puff. And I've done this in classes. I've brought people up and I take a little puffer, and I have some brave volunteers sit down, and I have them sit down in a chair, and I kind of randomly will puff their eye, and it takes about two to three trials, where I had usually I'd have a clicker in my hand, so I'd just be randomly click puff, they blink, and I'd wait and pause, and they'd be sitting there all nervous, and I'd go click puff. All right. By about the third time, I go click, no puff. And they're they're blinking and everybody's laughing. All right. So anyway, rabbits and you will very quickly get classically conditioned to a tone or something that's preceding this puff. Okay. So where in the brain is that being facilitated? Well, very specifically this area, the interpositus nucleus of the cerebellum. All right. So that little nugget right in the middle of the cerebellum is very crucial for this, facilitating this kind of memory. And it communicates with other areas, and other areas are communicating to it. And so, kind of some clever studies, teasing apart the role of these two. So there's, the red nucleus, in the hindbrain is also very important for these kinds of reflexive movements. And once upon a time, when we were talking about research methods, I said one temporary way to lesion something is by chilling it. Okay, so you can cool areas of the brain and effectively turn them off briefly, and then of course when it warms back up, they'll regain their function. So it's sort of like a temporary lesion. All right, so if you kind of turn off these two areas, and then when they're restored, they reveal interesting things about this eye blink reflex. All right, so if you do it to the red nucleus, okay, when you lesion it, they don't learn it. Okay, so even if they had learned it, and then while it's off, they're not blinking. All right, so the percentage of trials it takes for them to so they won't learn this task. So that would lead you to think aha, the red nucleus is important, because when we turn it off, it must, they don't form this eye blink memory. Okay, and then when when it warms back up and it gets restored, they'll immediately demonstrate that they've learned it. Okay, so that's tempting to make you think oh, the red nucleus is driving this. No, it's not, because this is in a control rabbit, it takes classical conditioning typically follows a curve like this. It's not immediate. Okay, it takes some trials. The first puff, and click, nothing happens. Second one, maybe a little bit, but not much. Like I said, maybe by the third trial, it's like click, puff, and already they're blinking to the sound of the click. And then every trial after that. So there's this steep learning curve. All right. And again, so this is an animal that's already learned to do this. When you turn off the red nucleus, it goes away. They're not responding to they're never learning, they're never reacting to the click anymore. Okay. But as soon as you turn it off, it just goes right back to where it was. All right. When you do the same to the interpositus nucleus, you get the same phenomenon. When it's turned off, no learning is being exhibited. But when it's restored, it restores back to the control condition. So anyway, that little elegant study demonstrates hey, they both are involved, but this one is the one that's storing and create, helping it's developing and then storing the memory. Okay, so kind of complicated. I hope that made sense. All right. I got no time. I got no time. So I guess I'm gonna just give you like the 5-minute, patient HM. Thankfully, we already talked about HM before, so I'm skipping to that part. We got to skip all the amygdala. I love the amygdala. We're gonna skip the amygdala talking about that. So a bunch of you are gonna pick the amygdala as your favorite brain part because every semester I get a lot of people picking that. No worries if that's your favorite. That's very understandable. If that's gonna be your favorite brain part, go for it. But anyway, it's sadly, I'm not going to talk about it now. We'll talk about the amygdala another time, but I'm not going to talk about it in terms of classical conditioning right now. So I want to just end by, the couple minutes that I got left. I just want to remind you guys about this major figure in memory. All right. So patient HM, to remind you, he was about 27 back in the 50s. He had a radical procedure done to try to cure his serious epilepsy. Drilled a couple of holes in his forehead, went in and swished out his most of his hippocampus. It turns out about 2/3 of that hippocampus. Remember, it's kind of curled up like that. So the tails, kind of survived this, vacuum procedure, sucking it out. Also, like I said, the amygdala is sort of the head of that beast. All right, so. They don't talk much about the fact that HM also had his amygdala on each side. They did this on both sides of the brain. So they took out the amygdala on each side and probably about up to here in of each hippocampus. And immediately after recovering from the surgery, they discovered, whoops, we shouldn't have done that because he had and then that's when we began to learn more and more about the hippocampus. So he had. We don't have time to watch that. So, it impacted his declarative long-term memories. Okay, so we learned all kinds of things about memory and strengthened some things that we were already beginning to learn about memory. So probably nobody taught us more about, and sadly in a sad way and indirectly sort of way than Henry Mollison. So we, strengthen our understanding of the distinction between declarative and procedural memories and semantic memories and so on. All right. So he had this inability to lay down all kind, any kind of new declarative memory. Very few examples of things over the next, how long did he live after that? Probably 40, 50, 60 some years. Okay. He died when he was in his 80s, about 10 or 12 years ago. And he was studied largely by this woman. And I think I told you the story about Suzanne Corkin and how I met her and she came out to Hawaii. This is her signing her copy of this book. So with no time left, I'm going to steer you to this book again. And if you want to know more if you want to know everything about HM's and his memory and memory research and just memory in general, get this book. If you're interested in like the fascinating case of patient HM, I think I told you this will be a disappointing book because Suzanne was not taken up with the sort of the gossipy parts of his life and his in this phenomenon. So there's she's the major reason why we didn't know his name until after he died. He was HM when I was a student. He was HM. He was HM until 12 years ago when he died. And we finally learned who he was, largely because she wasn't his legal protector, but after his parents eventually died, and there was some distant relative that still had like the final say in his care or whatever. But research-wise, you had to get through Suzanne Corkin to get to Henry Mollison to do research. Tons of research. He was amenable to doing research. We know a lot about him, and it's all in that great book. So I'm speed talking because I'm out of time. So anyway, thanks for being here today. Thank you, Olivia, for that great inspirational story. You guys have a good couple of days.